Hi, everyone. So we left when we were talking about the slit that was sending through green light to the sample. I want to briefly discuss that a bit more, and then we'll discuss the concept of a control in these studies, and we'll discuss more about the techniques of analyzing the studies. So in this case, at number 2, we are sending in only wavelengths of green light through to this sample. This slit is really ratcheted down to just let those wavelengths through. That doesn't need to be the case. The slit can be quite wide. The slit can cover anywhere from ultraviolet all the way up to the red. And in most cases, when you're starting on a study, you go wide and then you gradually narrow it down. We'll explore a little bit more about that. In this case, we're looking at green and what is transmitting through to the phototube. The phototube receives the amount of light energy that is not absorbed by the molecular compound in the cuvette. The phototube receives this transmitted light energy, the green wavelengths that come right through the molecular compound, and it converts the light energy into electrical energy. Now we're going to stop there for a second because the analysis is done in the photometric system, but we want to stick with the data for right now. We have in here a green solution, but there's not just the green solution. The green solution is with a mixer, and that's important because green solution can be very expensive. It would be great to put it with some water, which is very cheap, and maybe we can still isolate the green solution and identify it by its absorption. But if we have a mixer in with it, then the mixer is going to have its own molecular identification and absorption. Water is a compound of oxygen and hydrogen, and it can absorb wavelengths too. So the concept of a control here is that before we do any studies on our molecular compound, we make sure we know about the system itself and we know about the mixer. And we do that by using a cuvette that just carries the mixer. For instance, the first thing we'll do is we will put filtered water alone into this cuvette, and we'll see what the transmission and the absorption pattern is of the water alone. In that way, we can take a note of that and we can accomplish two things. We can note what our device records for the transmission and compare it to a known for water, for distilled water. I'm sorry, I can't really work that well with my broken arm. But in comparing our results for distilled water to a known result, we're making sure that our device is calibrated to a standard. That's number one. And number two, with those results, we're making sure that when we add in our green solution, we can subtract out the knowledge we have of absorption and transmittance of the water and just record the absorption and transmittance of the green solution. So using a blank accomplishes two things. It validates and calibrates our device, and it also gives us a standard by which we can look at the carrier mixture and plus the compound and subtract out the pattern of the carrier mixture to just leave the pattern of the compound for identification. Let's talk about what we've been saying about transmitting the light energy versus absorbing it. And this brings into mind what's going on the photometric side. The photometric side will display two scales, and you can choose between either one of them. Most of the time in biology, we will use the absorbance scale, known as the A scale. So in other words, whatever doesn't come out through number 3, is absorbed by the compound in here. And the photometric system can do the analysis to say, I put in wavelength 39 and wavelength 539, and I put in wavelength 541.5, but I only got 60% of one back and 39% of another. And it will give you a scale of absorbance on what did not come out and hit the phototube. That's a form of analysis that the photometric system can do. It's often used for biology. In other cases, and I teach astronomy, we use percent transmittance or emission spectrum or emission scale. We use exactly what comes through and hits the phototube. Just differences in what we're looking for. And in biology, most of the time we use the absorbance scale, which is a calculation of what comes through minus what went in. The absorbance is also called the OD, or the optical density. And you will hear both terms used. Mostly you'll hear A. But the very important thing to note is that absorbance is one way of looking at the data, and transmittance is another way of looking at the data. They are exact opposites. The compound stays the same. It transmits what it doesn't absorb, and it absorbs what it doesn't transmit. So you could look at these two scales and just see opposite data that would still be identifying data. In biology, though, we usually go with this scale. Now, when we look at the absorption spectra, it can look, and we looked for absorbance peaks. The absorbance peaks in a compound's analysis are like fingerprints to a person. They're unique to the person. So that this absorbance spectrum for chemical A used a slit that was wide open between 400 nanometers at the ultraviolet range and 700 nanometers at the infrared range. This is a wide open slit, often seen when you're starting out. You start wide and get narrow. This has a peak of approximately, probably 540 nanometers, and it has an absorbance scale that looks like it's around 0.66 or so. This tells us a bit about the compound, but it's too broad. There could be many compounds that have something pretty similar to this. We can't rely on this broad absorbance pattern. And in fact, you need to often break down the compound because it may have more than one absorbance peak. It could peak here and here. Remember, the more molecules or different molecules that you have in your compound, the more peaks you may have in your compound. And you'll have different levels of these peaks based on the amount of molecules of the element in that compound. So there's a lot that can go on, and in particular, this chemical B looks at the same scale, 400 to 700 nanometers, but it has two compounds, probably a more complicated compound right there. We can start to narrow things down from here to get a better feel for the ID. You could send a second sample of compound A into the cuvette and into the spectroscopy device, and maybe this sample would tone down that slit to only look at maybe 525 to 560. A narrower range. Maybe you send chemical B through and you've got something around 585 that you're targeting, but you go kind of wide, maybe 485, and you go kind of wide and you go 465 to 505. Maybe for this one, you go 625, but you keep it a little tighter because this peak is so sharp. Maybe you go 620 to 630 or so. All right, so you get a feel for what you can do for the next range when we are going to be narrowing down this, this fingerprint of this compound. As you narrow it down, you compare it to knowns, and you see that your chemical A looks a lot like a certain compound that you would flip through, and you flip through these knowns to get something that shows a peak just like this. Or when you get it back down, you might see that this peak actually divides into 520 and 530, but you don't see it over this broad area. So you go narrower and narrower and narrower. Next video, we're going to get into concentrations of the unknown in the solution and Beer's law. I'll see you on the next video.